Hi, and welcome to my presentation. My name is Thomas Hubauer. I am a portfolio manager for Knowledge Graph and Semantics at Siemens Technology. I'm also technical lead for an application field called data readiness. And in today's presentation, I would like to share with you how we at Siemens, how our path at Siemens looks like, getting from data to autonomous decisions using the technologies and processes that we have developed as part of our application field data readiness. Digital twins are everywhere. However, building a digital twin can be really expensive. Picking just one example from our business, it's a typical situation that it can take an expert 2 weeks to build a digital twin of a system. For instance, in this case, an as-maintained bill of material, which he needs, for instance, in SAP, as a requirement for some business process building on that. So there's a huge barrier to actually start working with the digital twin. However, what are those digital twins and where do they reside? Typically, the digital twin doesn't exist in one single system which you could use as a source. Instead, the information required to build a digital twin is distributed across a variety of systems. We like to classify the different system and types of data they contain into 1D, 2D, and 3D data. 1D data for us is the typical structured type of data. You have entities, you have attributes. So that would be all the typical corporate IT systems you find. It's customer relationships management, but also very use case specific systems such as configurators for certain products. On top of that, we have 2D data. This is diagrams and documents. Especially in context of brownfield data, it's obvious that a lot of historic data talking about your assets is not available in digital systems. Instead, you will find this information in service reports, in drawings, maybe even in handwritten documents. So there is a challenge to make this information, the data contained in those documents, accessible for your processes by making it part of your digital twin. Last but not least, 3D data would be computer-aided design and point cloud data. So it's kind of, again, getting a bit back to structured data. However, the complexity increases significantly, and we're really talking about huge amounts of data there. So knowing those data sources, the question is still, why is it so expensive to build a digital twin? And the key observation that we have been making over time here is that typically for each and every application, people start identifying the required information, finding the data sources, finding ways to extract the information, thinking about suitable target data models, writing ETL code to convert the data, thinking about integrating data from different sources, and all this into one application-specific target data model, which then serves one single application. This, of course, hugely drives development cost, because basically for each new application, you have to go through the whole process again. So instead, what we have been introducing at Siemens is the use of knowledge graphs as a technology that enables us to build what we call a digital twin fabric, which consistently and flexibly allows us to link over those different data silos and provide one consistent data model to all applications, which can then be reused. We like to use the term of a digital twin fabric here, which provides integrated and standardized access. And there's a number of building blocks that basically comprise this semantic digital twin model. First and foremost, and that's the orange part on the slide, we need a shared terminology. We need a shared data model. This alone can be a huge challenge, as we need to align all the different stakeholders, all the different sources, but also the needs of all those different applications, and bring this together into one data model that matches the needs of all those different users and applications and still remains consistent, even though it needs to bring together very different views. Also here, to avoid having to do this over and over again for like each collection of applications, we have been developing what we call an internal ontology library at Siemens, which comprises of a number of reusable building blocks that we use, for instance, to talk about bills of material. But really, it's not only limited to that. We also have modules coming from very different domains, for instance, to talk about buildings. Secondly, of course, what we need is the instance data. And this is kind of the middle and lower part of the graph you see. The way you can envision this is that basically for all those different sources, we first find ways to take their data and map them into a potentially intermediate model, which is already has some level of semantics attached, but might not yet be our final model. Then in a second step, the task we have to solve is basically bringing those local models together and align them with the one shared model, which is given by our shared ontology. On the one hand, this means mapping attributes, finding ways to express relations given our target data model. But there's also more to it, because typically your different data sources will not be talking about distinct entities. They will be talking about different aspects of the same entities. So one problem, one challenge we have to solve on the go is what we call the entity reconciliation problem. This means, based on the information that the different data sources give us, we need to identify when two sources are talking about the same entity, and we need to merge this information. By doing this, we need to take care of things such as consistency. So when two sources talk about the same entity, as long as they talk about different attributes, everything might be fine. If they talk about the same attribute, but give us different values, then we need strategies to cope with that. Those strategies might even be use case dependent, or dependent on the IT environment, such as a certain system being declared the lead IT system. By solving all those problems, what you get is basically one consistent representation of the information about your entity or entities coming from all those different sources. And this integrated and standardized representation is what we call the digital twin. And yeah, it's represented as what we call the so-called digital twin fabric, which gives us one standardized way to access all this data. Just as a quick note, bringing this information together doesn't always mean that we put everything together into one single data silo. That might make sense for information which is kind of static and not changing a lot. However, in other systems, you might also have highly dynamic information, or it might be complex rules which you do not want to export and be able to take care of yourself. So some of those sources might also be connected virtually. So we are talking about federation or virtual data integration in that case. And this then allows us to basically leave the data in the original systems and only pull it on demand. Now, going one step further, it's not always the case that we need a full-fledged digital twin, including all this information to start creating value. And that's really important. That's a learning we had over time. If you wait for the perfect one digital twin and only then think about creating value, then nobody's willing to pay for it, nobody can afford it, and it's really hard to convince business and management that they want to invest. Therefore, from our experience, it typically helps a lot to start with quick wins. And just to show you a few examples, one example could be what we call master tag lists. So looking primarily at the structured sources, which can typically be easier to handle, and basically consolidate different tags or attributes you get from them, bring them together in one list, and making them accessible in one consistent way. Already this can create a tremendous amount of value for a user. On top, a potential next step is including information that's contained in documents. One typical example, which I will go to in a bit more detail later, is P&I digitalization. Here, what we're doing is basically extracting semantic information from 2D drawings, so-called piping and instrumentation diagrams, and bringing this information together with the information we already get from the structured systems. And then on top, you can, of course, go beyond and bring in 3D data and maybe even other types of data, be it time series, whatnot. The important part is really start creating value early. So now I would like to show you one concrete example how bringing together structured and unstructured information from piping and instrumentation diagrams is creating value at Siemens. This example is coming from our colleagues at Siemens Energy, who've kind of been also very helpful for us and a really great partner for us to build up all the technology stack and all the processes that I'm showing here. The challenge that our colleagues at Siemens Energy were having, just like similar to the example of the statement I had on my very first slide, is they need an as-maintained bill of material in SAP. This is a requirement for some other business processes building on it. However, the information they need to do to create this as-maintained BOM is coming from at least 3 different sources. We have Teamcenter or SAP, which is structured information talking, for instance, about design BOMs. We have drawings, in this case, P&IDs. They help us understand systems we're not building ourselves, so where we do not have design information in a structured format. And last but not least, service documents. They help us to understand how the system has evolved over time. As you can see in the drawing, we need to apply a number of different technologies, transformation and mapping for structured data, image recognition, symbol detection, and so on for the drawings, but also natural language processing for service documents to extract the required information and then integrate it in one semantic model where we have to address all those challenges I mentioned already, entity resolution, consistency checking, and so on. We like to use knowledge graphs as the data structure where all this integration happens. And basically, this knowledge graph could be understood as maybe, if you want to say, the digital twin of the turbine. I'm emphasizing the V because for me, there's not one digital twin. There can be several depending on the aspects you want to look at. But this is kind of the richest representation that we can have of this turbine. From here, there's different ways we can proceed. In this use case, we're basically using queries against this integrated graph to export the target structure and bring the data into SAP. What I would like to emphasize here is in this graph, we have the full history of the turbine. So in this graph, you could basically like zoom through the lifeline of the turbine and see how it developed over time. This is great. This is exciting for me as a techie. For the business case, what we're doing is we're using the last known state. We're exporting the data. We're bringing it into the operational IT system. And based on that, repair and overhaul processes can be triggered. So this is a great thing, a great achievement technologically. What's in there for the business? So for the business, numbers show they have an 80% cost reduction for generation of as-maintained bill of material. Now, why maybe only 80%? As you can see here, we're striving for a very high degree of automation, yet it's not possible to have this fully automated. So there's a few specific points where we want the user to interact, where we want the user to tell us if things are correct. And so there's still some human involvement. Still, we kind of multiply the number of turbines one guy can work on by 5. So we're really creating a huge lever for business here. As a consequence of having all this information available, sales, mods and upgrades, parts sales, they are up to 90% faster, for clarifying quotes and understanding what could we offer to this customer, what should be the price, and so on. And also the quality of those quotes is improved, so we end up with a higher hit rate. The business is quite happy about this. I want to give you a bit more technical view just to have some idea of the type of data we're looking at. Here you're seeing service reports. And the red highlights show a bit the type of information we're interested in. As you can see, it's kind of relatively meaningless strings. So very often the extraction alone doesn't help. You need to bring this information together with data you have from other systems, such as configuration management systems, to tell you how to interpret the data. Moreover, the position in the document may give a different meaning to exactly the same string. So it's not just sufficient to extract any string and be happy. No, we need to keep track of where did it occur, in which context did it occur. And this is an automated pipeline we've built, which extracts this information, brings it into a structured format, and then again shows it to a human as especially part of information where our machine learning algorithms tell us, yeah, I'm not 100% sure. Why? Because for the use case I've explained to you, it's vital that we have 100% data quality in this step. Therefore, whenever the automated processes are not fully sure, we have a human check. So we have a manual QA process which builds on top of the automated part you see below: OCR, character recognition, NLP, text extraction, some data quality logic we are applying already. And then on top, when all this is done, we have a human look at the data and give us a thumbs up, thumbs down. Another type of information we're looking at is piping and instrumentation diagrams. The challenges we have to solve here is extracting symbols, understanding all the text that those symbols are annotated with, understanding how to which symbol certain text belongs, but also extract the piping, so which things are connected. And all this in the end gives us, basically a bill of material and connectivity information of a certain subsystem of our turbine. Again, here we need extremely high quality data to be extracted. Therefore, what we've built, and you see live screenshots of the system here, we've built an interactive system that displays the extraction result to a user, again, in the current version, even with highlighting of certainty, and then allows the user to say, yeah, I'm happy with that. No, I want to change something. And this is where active learning comes in, because if a user tells us, no, the symbol is actually not a motor, but it's a certain type of pump, then we will collect this feedback and we will retrain our models. So the more people use the system, the smarter we will in the end get. Taking a step back, what I've shown you now is what we would call a data companion. It automates the process of extracting data and bringing data into a valuable format. Obviously, this is by far not the end of the journey. For me, it's kind of the starting point. We have this great digital representation of our asset, and there's so much more we can do. One still relatively simple example would be smart search and question answering. And looking at the use case I've just explained, I'll never forget the excitement I saw in the eyes of the turbine technicians when we showed them a graph just like the one you can kind of see on this small picture, which allowed them to understand which type of equipment is deployed where, and they could flexibly slice and dice the data and really get a fleet level view of what they're doing. Yet there's more, and one quick other glimpse I want to give you is recommender systems, especially with an emphasis of also being able to explain the decisions. Jumping to a slightly different domain here, we're now in industry, we're in configuring industrial IT systems, or industrial OT systems, industrial automation systems. And here, what we've developed is so-called sequential recommenders. So it's a challenging task to basically, even if you have your components, to set them up in the proper way. And we are using the digital twin of basically the system. So the digital twin with all its technical features. We're using historic data of user operations to then build a graph, knowledge graph of the system. And we're using a task called link prediction to basically make proposals for the user of what he or she might in the end want to do. As a result, we can show that we get an order of magnitude reduction in configuration time, while at the same time giving the user very application-driven proposals for components, and even being able to give recommendations for hitherto unseen items. So to close, for us at Siemens, we've realized creating digital twins is highly expensive. I've shown you what we call data cleansing as one example. We have different technologies to tackle this using industrial data models, collections of ontologies, and so on. And for us, graphs are a core ingredient where we bring together all this information in what we call the digital twin fabric. As a result, we have this integrated, rich, context-enriched data, which provides huge opportunities for business, ranging from relatively simple things, such as having a bill of material available, to complex machine learning-based applications that can, for instance, be based on recommended systems. With this, I would like to close. If there's any questions, if this caught your interest, I'm happy to hear from you, also to get your feedback and to learn what you guys are doing. My name is Thomas, and as mentioned, I'm an application field lead for data readiness. Happy to hear from you. Thanks a lot.